But we are lucky. Lucky in the sense that shear xy is equal to shear what? Yx. Right over here, if this is the closest, okay, you can see the difference in length, yes or no? Right? This difference in length is the one that is going to induce slip the slip which is parallel to the schematic layers. Okay, so you ask me, Eugene, what are all these layers? Let's say if you were to bend thin sheet of plywood, okay, you put 5 sheet, and when you push it down, right, you will see that along this direction that I'm highlighting in yellow now, you see that the distance get bigger when your force gets higher, right? This distance over here, right, that I'm highlighting in blue now, the vertical one, it did not change in dimension. So if there's no change in dimension, right, there's no what? Strain at all. Yes or no? Okay, so this is how shear will induce failure. Okay, now there is only two formulas. Okay, there's only two formulas in this chapter. It's interesting. The topic, which is the hardest, has only two formulas. Okay, so I'll write for you now. Okay, so is we have what we have is horizontal shear per unit length. Okay, and we also call this the shear flow, also known as shear flow. Okay, I'm going to call this AKA, also known as, okay, shear flow. Okay, so shear flow is the more common name that we use, and the formula is Q is equal to VQ over I. Okay, so this is the general formula. Okay, this is the general formula. Okay, I will write the more complex later on. The more complex form. Okay, more complex form. Okay, more complex. So I'll write based on the shear stress weight. Okay, so you have horizontal. So V or Q we know is the shear flow. Which is in Newton per meter. Okay, and then we have V is your shear force. Okay, Q, capital Q, is the first moment of area. Okay, first moment of area with respect to the centroid axis. Okay, so the formula for first moment of area is Q is equal to A y bar. Okay, where A is defined as the A is the defined area. By the way, the first moment of area, the units is in meter cube. Okay, so the defined area is in meter squared or inches squared. Okay, and then your y is the distance between the centroids of the defined area the axis or to the central axis. Okay, so this is in meters. Okay, that's why it's in meters cube, and I is going to be the structural global, okay, second moment of area. Okay, let me zoom out, then you can see. Okay. So if we write the shearing stress, okay, so that is the shear flow. Later on, I'll tell you all what is actually the shear flow. Okay, I'll tell you now. Shear flow is the flow, how the shear stress is flowing. Okay, all right. I know it sounds stupid. Okay, hear me out first. Okay, it's how the shear flow is defined as the direction on how the shear stress. Oi, something happened. Undo. Okay, on how the shear stress is flowing within the cross section area of the structure. And it's very important to design the shear flow. Okay, and it's very similar. I'm going to put down here bracket, similar to fluid flow. Okay, very similar. Okay, right. So I is the second moment of area. Now the shear stress, the shear stress is defined as shear is equal, and I'm gonna write out the two axes. Okay, in the end of the day, our analysis is in 3D. Okay, so the shear flow is equal to, or the shear stress is equal to Vy over Izz Qz divided by T. Okay, plus or minus Bz over Iyy Qy divided by T. Okay, so I want you to learn this trend. Okay, there is a trend on laboring, right? There's a trend that's going on. What do I mean? In bending moment, right, which we have just completed, we call stress is equal to Px over A, right? Plus by My over what? I what? Yy multiplied by Z. Then it's minus Mz over Izz multiplied by Y. Okay. I'm still a firm believer, do not worry about the plus or minus. Use your moment vector. Down here also, don't worry about the plus or minus. Okay. You use shear force or you will, sorry, you use the direction of the shear flow to determine whether it's a plus or minus. So the plus or minus over here, okay, is dependent on the shear flow direction. Okay, so the shear flow over here is Q, okay, and direction. Okay, so how to remember this formula? So I usually use this to remember, you know. Moment when it's my, you divide by iyy. Mz divided by mzz. For shear stress or shear flow, by you divide by what? Izz multiplied by what? Qz. When it's vz, you divide by iyy multiplied by qy. Completely opposite from what? From your normal from your bending moment. Okay. So by is the shear force. Wait, something happened again. Go on. I think it's me. Is the shear force acting in the y-axis. Okay, so Vy is the shear force. So Vz is the shear force acting in the z-axis, right? T over here is the thickness of the beam, no, of the cross section. Okay, so all these are in Newton, and this is in meters. Okay, so the next thing we're going to look at is we're going to look at the shear stress in thick wall. Okay, so we're going to look into the theory. We're going to go into the theory of shear stress in thick wall. Okay, so I've posted the diagrams. Okay, we're going to use this diagram over here. Okay, so we're going to use this diagram. So what on this diagram, okay, we are looking at the cross-sectional view. Okay, we are looking at the cross-sectional view, and the shaded region over here. Okay, you can see a different shaded region. This is the area. Okay, where shaded is the area of interest. So what I mean by area of interest is the area that you are interested to see what is going on to the shear stress. Okay, so we're going to derive. Okay, we're going to derive the shear stress equation. And for this case, our shear force, okay, where it's orientated at this current moment, the shear force is in the y direction. Okay, so the shear force is coming perpendicular down. Okay, I'm going to stop here. I will see you guys again at 10:30. Okay, I'll stop recording. I'll still be around. If you have any question, please stay behind and ask me.